Good evening, all. So, welcome to the uh, problem solving session, week 10, week 10 of the course Geotechnical Engineering 1, uh, taught by Professor D.N. Singh from IIT Bombay, from the Department of Civil Engineering. And I am Yogendra Narayanan. I am a PMRF research scholar who will be conducting these sessions. So, to give a brief overview of this about these sessions are intended to make the learners proficient with the subject, contents of the subject that are taught every week uh, by solving some of the problems, uh, solving some of the problems by applying those concepts that have been taught on the in the corresponding week so that it might be useful for the learners to uh, approach the problems in NPTEL exams as well as in their future endeavors, professional endeavors like competitive exams and uh, further professional career. So this to give a brief overview of or a quick revisit of the concepts that have been taught in week 10 of this course is to compute the in situ stresses that acts on a soil mass due to external loading. Several theories that have been formulated to compute these stresses, their various assumptions, and both analytical as well as graphical methods. Analytical as well as graphical methods. And so with this as background, we will be solving some of the questions which will be applicable both in for the fundamental understanding as well as the real life applications. So with this, we have some basics of theoretical questions followed by the numerical problems. I would like the learners to actively participate in these sessions and ask questions, and you are free to interrupt whenever or wherever uh, you feel co- you feel more clarity is required, or and the learners are welcome to engage in uh, active discussions regarding these topics, so to give their insights also. So coming to the presentation, so we will start with the questions. So what are isobars? So first one is, what are isobars? The options are lines connecting points having the same temperature. Option B, lines connecting points having same pressure. Option C, lines connecting points having same volume. And option D, lines connecting point having same water content. The question is, what are isobars? Lines connecting points having same temperature. Lines connecting points having same pressure. Option C, lines connecting points having same volume. And option D, lines connecting points having same water content. So coming to this, it is bar. The keyword bar corresponds to pressure. Hence, isobars are lines that connects the points having same pressure. So coming to the other options, it is for your knowledge. So lines connecting having same temperatures are known as isotherms. And these are isobars. volumes are iso plates. Same moisture content is iso heights. So iso in the sense iso corresponds to equal. Terms is temperature, bars is pressure. Isoplates refers to contours of lines connecting points having equal volume, and isoheights are lines connecting points having same water content. I hope this is clear. Coming to the second question, which of the following is not an assumption associated with Boussinesq's theory? Which of the following is not an assumption associated with Boussinesq's theory? So, as we all know, Boussinesq's theory is one of the most common theories that have been employed in soil mechanics to compute the increment in stresses beneath the soil mass due to the application of external load on them. Right? So, the first and main assumption is soil mass is homogeneous and isotropic in nature. And option B is elastic and semi-infinite. The soil mass is considered to be semi-infinite and the deformation is considered to be elastic. So this assumption is also right. Coming to option C, Hooke's law is valid. Since the soil mass is considered elastic, obviously it has to obey the Hooke's law because it is within the elastic limit, stress is directly proportional to strain. And biggest coming to the fourth option, the weight of the soil mass is considered. So if it is the weight of the soil mass is not considered because it is purely of a geometrical terms, any of the parameters uh, corresponding to uh, weight or density or stiffness of the soil is not considered here. So the option which is not an assumption of Boussinesq's theory is option D. The weight of the soil is considered. That is not an assumption. Right? I'm clear now. To the next part. Now we will solve some of the problems associated with it. If a point load of 100 kilonewton is applied on the surface of the ground, what would be the stress at a point 3 meter below the load application point? So we will first conceptualize the question. So this is a ground condition and a point load of 100 kilonewton is applied, right? So that will be our Q. Now this is the question that has been given. Now what would be the stress at a point 3 meter directly below the load application point? So let us directly below the load application point, let us draw an imaginary line to depict the uh, line directly below the point of application of the load. Now let us consider a point P here. which is at a depth of 3 meters. That will be your Z. Now we have to apply some direct Bossinus theory, which states that the stress at particular point, that is at P, is given by 3q by 2 pi z square to 1 by 1 plus r by z whole square divided by whole power 5 by 2. Now, if we see the question, what would be the stress at a point 3 meter directly below the load application point? So here there is no eccentricity in the point for point of consideration. So hence R will be, so we know that Q is 100, Z is 3 meters, R is 0. Alright. Now this entire term will be tending to, not tending to 0, it will be equal to 0. And the relation will become as 3q by 2 pi z square. Now substituting the values, 3 into 100 divided by 2 pi into z is 3, 3 square will be 9. So let this be 50. Please compute the values. This will be 3, it will be 50 by 3 pi. Please compute and let me know. So it will come to about 5.31. What is unit? This is kilonewton. Other all are constants. Z square is meter square. It will be the stress kilonewton per meter square. All right. This is the answer. Sigma Z at P. Right. Now coming to the next question. Hope uh, hope it is clear. So the major point to be noted is in solving the problems associated with geotechnical engineering, please keep this in mind whenever you approach such kind of problems. In as far as soil mechanics and foundation engineering is considered, it is very very uh, prudent to formulate the question in form of a diagram to understand what is the situation that has been given in order to apply your relationships suitably and appropriately. All right. So coming to the next question, a 50 kilonewton point load acts on the surface of an infinite elastic medium. What will be the vertical pressure in kilopascal at a point 6 meters below and 4 meters away from the point of load application. All right. Now formulate this. This is the ground surface, and on the surface, a 50 kilonewton load acts, and we have to find, consider the depth. Depth is 6 meters, and point is 4 meter away from the point of our load application. So this is the point. Let this be point P. So this is 6 meters. This is Q. This is Z, and this is R. Just a minute. There is a sorry. So coming back to the question here. So this is R is equal to 4 meters. Now let us apply the same Boussinesq's equation. Sigma Z at P is defined as 3Q by 2 pi Z square 1 by 1 plus R by Z whole square power 5 by 2. Now you can see from this relation our answer to this second question. So here nowhere the property of the material is getting re reflected. Alright. So that is, it is blind of the material properties. Right. So substitute these values in this equation. 3 into 50, 2 pi into 36, 1 divided by 1 plus 4 by 6 square whole power 5 by 2. How much we are getting? 3, 12, 2, 25. You get 25 by 12 pi into 1 by 1 plus 2 by 3 whole square power 5 by 2. Computing this, just remove this. So we compute sigma z at P is equal to 25 by 12 pi divided by, this is 4 by 9, 1 by 1 plus 4 by 9, power 5 by 2, which will be 25 by 12 pi into 9 by 13. So 5 by 2. Calculate the answers. 9 divided by 13. 25 divided by 12 divided by 5 will be almost 0.26 kilopascal. Sigma Z, very less. Thus the load is also very minimal. Coming to the fourth question. A square column sized 3 by 3 is carrying a load of 5 meganewton. A square column sized 3 by 3 meters is carrying a load of 5 meganewton. What would be the stress at a point 4 meter below the footing? What would be the stress at a point 4 meter below the footing? Right? Now, in order to understand this, just shift these two questions. Next slide. Fine. Now, coming to the question, let us draw the diagram. So, square column. So, it is a square column area. It's carrying a load of 5 mega Newton. Alright. Now this is 3 meters. Now coming to the dispersed angle. Now, so the load will be distributed in this direction. So when the angle of distribution is 30 degrees. Alright. Now here we have to calculate. Now the stress dispersion will be sigma z at a point P. At a point P, 4 meters depth. Will be Q applied by divided by the range of the footing here will be expanded. So this will be 3 meters plus x plus x. All right. In the same manner, since it is a square footing, it is a symmetrical manner outside into the plane. So it will be y y and 3 meters. Now in this case, it will be 3 plus 2x into 3 plus 2y. How to calculate x and y is that we know the dispersion angle of 30 degrees. Now we know this is 4 and you can calculate this. You need tan 30, sorry, tan 30 degrees will be opposite by hypotenuse, sorry, adjacent. And similar way on that side, tan 30 will be opposite by adjacent. Now substituting this tan 30 x by 4 y by 4, calculating it, it will be 4 into tan 30 degrees. Tan 30. 4 into tan 20 degrees. It will come to around x will be y is equal to 2.31. Now substitute these values in those so that we will get the stresses. Q divided by 3 plus 2 into 2.31 square. Substituting it, sigma z 5000 kilonewtons divided by 31 into 2 plus 3 power 2. will get us 58.06. So dividing it by 50,000, it will be coming as 86.12 kilopascal. So this is the stress that acts at a point 4 meters if we consider the angle of dispersion to be 30 degrees. All right. Coming to the next question. The construction of Newmark's influence chart. The construction of Newmark's influence chart, the number of annular areas are 10 and each is divided into 20 sectors. Then what would be the value of the influence factor? So in order to understand the working of Newman's influence chart, we have to understand how it is constructed. So a Newman's influence chart would consist of 10 annular circles. So in this they have given a loading area. So how it is done is, first a larger area, uh, circular area is considered, which is divided into several segments, small segments. So each segment will correspond to a particular loading factor. So that is known as influence factor. So, and then the plan of the foundation or the plan of the uh, area where the loading acts, that is, it is a aerial loading, that is two-dimensional loading. The entire plan of those loading is placed or superimposed on those influence chart, and then the number of segments that the area covers is calculated, and then it is multiplied with the influence factor. So first, for Newman's influence chart is calculated, first we have to calculate the influence factor. So it consists of a single circle first, larger circle. This is the entire area, and it is divided into 10 annular circles. That is concentric circles. Right? 6. So like this, it will be 10. 10 concentric circles. So now, if the entire contribution is 1, what will be the contribution of a single concentric circle? It will be 1 by 10. So if 1 kilonewton acts, so how much kilonewton acts at each concentric circle? It will be 1/10 of the total one. Now, this entire circle is divided into 20 sectors. One, this is one sector, two sectors, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So there will be 20 sectors here, and hence from now this is each segment. So to highlight here, so this will be each segment. So the entire considered area, not considered area, but entire reference area is divided into such 20 into 100, 100 divisions. So that is 200 segments will be there. So if it is a single, if 1 kilonewton acts in it, so the total, the load acting uh, in a single segment is 1 by 10 further divided by 20. All right. So the influence factor is 1 divided by 10 into 20, which is 1 by 200, which corresponds to 0.005. All right. Now, how this is calculated is that, so we know the, now consider uh, a irregular area of loading. All right. Now let us consider this is the area of loading. This is how it is loaded. All right. Right. Now, now we let us consider it is loaded at some 100 kilopascal loading, uniformly distributed load, but in a irregular shape. So now in order to calculate this, we have to count how much segments that this area has covered. How much segment this area has covered. So if you count it, and just you have to multiply this loading into this influence factor into the number of segments that the loading area covers. So that is how it is calculated. So in the next question, we will be seeing how it is calculated. Now, coming to the next question, a Newmark's chart has an influence factor of 0.01. When plan of circular footing is superimposed on the influence chart, the number of sectors occupied by the footing on the Newmark's chart was found to be 15. Then what would be the stress at the point of interest if the low footing is carrying a load intensity of 1500 kilopascal? Now the influence factor instead of 0.005 it is 0.01. So that may vary based on the type of number of annular circles and the sectors divided are considered. Now you see here there is a circular loading, circular footing, and it is uniformly distributed load in that of 1500 kilopascal intensity, and it covers 15 sectors. So somewhere it will be like this. So number of sectors n is 15, influence factor is 0.01, and the load intensity q, or this is a uniformly distributed load, q is 1500 kilopascal, and hence the stress will be 0.01 into 15 into 1500. So that will come into 225 kilopascal. So this chart is then constructed for each and every tip, or it is for so at a particular point of interest. So we have this 225 kilopascal of stress that is acting, which is this is the graphical method, and Bossinus theory and Westergaard's theory etc. are analytical methods. All right. Hope it is clear. So just a minute, I will be back. Sorry for there was an emergency. So coming to the next question, the change in vertical stress in the soil mass estimated by Boussinesq's equation when Poisson's ratio of the soil changes from 0.25 to 0.40 will be. The change in the vertical stress in the soil mass estimated by Boussinesq's equation when Poisson's ratio of the soil changes from 0.25 to zero point 0.4 will be. So here we have seen from the assumptions of the Boussinesq's equation or Boussinesq's equation from estimated by equation of Boussinesq's theory. So it does not depend on the Poisson's ratio of the material. So here the question will be more precise. Change in vertical stress in the soil mass. Here you can write it as at a particular point. At a particular point. Particular point. Particular point in the soil mass estimated. So the change will be delta sigma z will be equal to 0. Since delta sigma is independent of Poisson's ratio mu, right? So in some books, Poisson's ratio is designated as mu. In some books, it is designated as nu. So you can follow any of this. So this is the major. Uh, this is the reason. So all right. Now coming to the next question. A uniformly distributed line load of 500 kilonewton per meter is acting on the ground surface. Based on the Boussinesq's theory, what will be the ratio of vertical stresses at a depth 2 meter to that at 4 meters directly below the load? The uniformly distributed line load of 500 kilonewton per meter is acting on the ground surface. Based on Boussinesq's theory, what will be the ratio of vertical stress at a depth of 2 meter to that of 4 meter directly below the load? Now, this is a line load. So, we have to apply Boussinesq's theory corrected for the or improved for the line load. It is not corrected, it is improved. Because the Boussinesq theory was in principle intended to address the increment in stresses or the change in stresses in the soil mass when a point load is applied on the surface. So now then it has been improved by applying the principles of integration to line load as well as uniformly distributed load in a rectangular and circular areas. So for line loads, sigma z will be, so you can, this is a line load. So it corresponds to 500 kilonewton per meter. So then they want ratio of vertical stress at a depth of 2 meters to that at 4 meters directly below the load. So let this be the line, which is, this is continuing both the sides, and we need at a depth of 2 meters and at the depth of 4 meters. So there is no eccentricity here. Now the relationship for calculating the stresses is sigma z is equal to 2q by pi z into 1 divided by 1 plus x by z square the whole square. Now the x is that, let us consider a point away, eccentricity. So the radial distance r will be r and this will be considered as x. So x here is 0 and hence the entire term will be 0 here, and hence sigma z in this condition will depend upon 2q by pi z. So now q remains constant. Uh, now that means q remains constant, 2 remains constant, and pi remains constant. So that means we can write it as sigma z is in this condition is directly proportional to 1 by z. Now sigma z1 z1 is equal to sigma z2 z2. You can write like this, right? Now we know Z1 and Z2 are, since it is now sigma Z at 2 meters by sigma Z at 4 meters will be, the ratio will be 1 by 2 divided by 1 by 4, which will result in 2. Right? Ratio is 2. Now if we can calculate what is the actual stresses here. Sigma Z at 2 meters will be equal to 2 into 500 by pi. Z is also 2. 500 by pi, which gives us a value of 159.16 kilopascal. Alright. And sigma Z at 4 meters will be half of it, which is 79.58 kilopascal. And the ratio is 2. Alright. So that is how it is applicable for line loads. Alright. Now coming to the next question. The vertical stress at a point below the corner of a 1 meter by 2 meter footing is 50 kilopascal. What will be the vertical stress below the center of a 2 meter by 4 meter rectangular footing at the same depth and same load intensity? So for that we have to consider initially one meter and 2 meter, and let us consider this corner. So this at the depth, same depth is, some q is 50 kilopascal. Right. Now they are asking to consider a footing below the center of a 2 meter by 4 meter rectangular footing. So what we can do is, so the width and length is 2 meter by 4 meters, which is double the dimensions of this particular square. So now let us extend this to another 1 meter, another 2 meters, right? So here we have 4 squares. This is 1, this is 2, this is 3, this is 4. Sorry, not squares, rectangles. 4 rectangles, and each corner of this rectangle has 50 kilopascal load. Now, if we fill the loading corresponding to this rectangle in all the 3 remaining parts of this new footing, so this will contribute to, so let me write in a better way. So this is contributing 50, right? Now similar way, the dimensions are same. This is 2 meters, this is 1 meter, this is 1 meter, This is 2 meters. This is 2 meters. This is 2 meters and this is 2 meters. So similarly, it will contribute 50 and this will contribute 50 and this will contribute 50. All right. So ultimately, this point where the entire corner of this rectangle lies becomes the center of this entire footing of 2 meters by 4 meters, and hence each 50 gets added on this particular point, and hence the load acting in it will be 4 times 50, which is 200 kilo Pascal. All right, this is the answer. Now coming to the next question. A concentrated load of 1 kilonewton acts on the surface of the soil mass. A concentrated load of 1 kilonewton acts on the surface of the soil mass. Determine the ratio of the vertical stress at depths of 1 meter and 3 meter just beneath the load. Just beneath the load. That is, there is no ratio, that is radial distance. So let us formulate the diagram. So this is a point load of 1 kilonewton, and there are two depths at which needs to be calculated, which is 1 meter and this is 3 meters. So sigma z at 1 meters divided by sigma z at 3 meters. So here we know that sigma z is 3q by 2 pi z square. Since r is 0, z is 1 meter, comma 3 meters, q is 1 kilonewton. Now, if we consider 3 into 1 divided by 2 pi into z square 1 square divided by 3, 1, 2 pi into 3 square, which is 9. So everything will get cancelled, which will come to 9. Now, if you want to compute the magnitude of the stresses, just 3 into 1 by 2 pi, just 3 by 2 pi, which will come approximately to 0.5. Which is 0.477, and sigma z at 9 meters will be 0.477 divided by 9, which will come to 0.05453. This is kilopascal. This is kilopascal. All right. Now coming to the next question. Same question has been asked again. So And this one. If the point load is doubled, so this question is already solved. So if the point load is doubled at the ground level, then what would be the stress at a point 3 meters directly below the point of application? So same here. This Q, the point of interest is P, which is at a depth 3 meters. Now, since R is 0, this is Z. We know that by applying Bossinus theory, we know that 3Q by 2 pi Z square. Now, Z remains constant, 2 pi remains constant, and 3 remains constant. Sigma Z is directly proportional to Q. So, if Q increases 2 times, sigma Z increases 2 times. So, the answer will be, what would be the stress? It will be 2 times. 2 times the sigma Z corresponding to Q1. Alright. Now coming to the next question. So 3-point loads 1000 kilonewton acting at A, 800 kilonewton acting at B, 600 kilonewton acting at C. So earlier there was a point are arranged. Calculate the vertical pressure at a depth 3 meters under all the point loads. Now it is a fairly a comprehensive exercise which we are going to do here. Now what we have to do is, we know that A is acted upon by 1000 kilonewton, B is acted upon by 800 kilonewton, and C is acted upon by 600 kilonewton. Now, and the Z value is 3 meters. Alright. Now we have to first let us calculate the stresses acting under point A corresponding to this depth. Now here sigma Z beneath A is getting contributed by QA into IZ. Sorry. So here before using this, let me define the terms here. QA is 1000. So the units are same here. Units are kilonewton for loads and meters for length. QB is 800. QC is 600. All right. Now we know that sigma Z is equal to 3Q by 2 pi Z square into 1 by 1 plus r by z whole square by 5 by 2. Now here except q, other entire thing, that is this entire thing, as we know, is defined as q into iz. Iz is the kind of influence factor, right? So those influence factor we calculated from graphical methods. This influence factor we have calculated it from analytical methods. All right. So just this is for information. I'll just erase it for the considering the space requirements which we have here when we calculate it. So first let us calculate the stresses beneath A. All right. Now it will be QA IZ influence factor due to A plus here also it is acted by a load and point C is also acted by a load, and in addition to the effect that this 1000 kilonewton has on this point, the effect due to the load acting at point B and point C also will contribute to the stress acting at at 3 meters beneath the point A. So it will be QB into IZ into B plus QC into IZ into C. Now coming to this solving, so this way if we expand this, it will be 3 into 3QA by 2 pi Z square. Z is 3, 3 plus, sorry, plus 3QB by 2 pi Z square into 1 by 1 plus R by Z whole square power 5 by 2 plus 3QB QC into 2 pi Z square into 1 plus 1 plus R by Z square into 5 by 2. Alright, now here R will be, Z will be the same entirely. So R will be the radial distance between the point A and point B is 4 meters. So R will be 4 here. And here the radial distance between C and A will be this one. So hence this will be 3 square plus 4 square, which will be 5 meters. So R here will be 5 meters. Hence now you can take this 3 by 2 pi z square outside. 3 by 2 pi into 9. So which will eventually give 1 plus 6 pi, 1 by 6 pi into 1000 plus 800 into 1 by 1 plus 4 by 2 is 4. 2 square is 4 or 5 by 2 plus 600 into 1 by 1 plus 5 by 2 whole square or 5 by 2. Alright, now coming to this, let us take 200 outside. 200, that will lead us to, sorry, 200 by pi Okay, 100 by 3 pi into 5 plus 4 into 1 by 5 will be 0.2 over 2.5. It will be 0.18 plus 3 into 1 plus 2.5 square 6.25, 1 divided by 7.25, 0.007. So multiplying it, so 5 plus 4, 5 plus 4 into 0.18 plus 3 into 0.007 into 100 divided by 3 pi, which will give us 60.91 kilopascal. Alright. Now similarly, let us calculate this for point B also. Now sigma z at B will be QB into IZB plus QA into IZA plus QC into IZC. Now let us take this 3 by 2 pi. 3 by 2 pi z square, z is going to remain same, plus by 6 pi into QB is, so we need to write it. So 3QB by 2 pi z square plus 3QA by 2 pi z square into 1 by 1 plus r by z whole square power 5 by 2 plus 3QC by 2 pi z square into 1 by 1 plus r by z by z whole, whole square power 5 by 2. Now here same r will be 4 meters and here B to C r will be 3 meters. Alright. Now let us take this. When we take this, it will be 1 by 6 pi and QB will be, let us take this 200 also, so that it becomes 100 by 3 pi. This will be, since QB is 800, we have 4 plus 5 into 1 by 1 plus 1 by 5 power 5 by 2 plus 3 into 1 by 1.5, 2.25, 3.25 or 5 by, alright. Now calculating this, 0.2, okay, this is 0.018. There has been a small mistake here. This is 0.018. So in that case, it will be 5 plus 4 into 0.018 plus 3 into 0.007 into 100 divided by 3. Right? So this will come to 54. It comes to 54.04 kilopascal. Alright. Now coming to here, we will have the same 0.18. Sorry. Same. 0.018 into 5 plus 4 plus 3 into 1 divided by 3.25 power 0.053, right, into 100 by 3.5. So which will give us 4 plus 5 into 0.018 plus 3 into 0.053 into 100 divided by 3 pi. It will come to 45.08 kilopascal. Similarly, for sigma z at C, it will come to QC by IC plus QAIA plus QBIB. That will be equal to same. So here R A and C. R A and C will be 5, R B and C will be 3. So here this will be 3q by, this will be 100 by 3 pi divided by QC will be 600, for which it will be 3 plus A will be 5 into 1 by 1 plus 5 by 2 whole square power 5 by 2 plus 4 into 1 by 1 plus 3 by 2 whole square power 5 by 2. Alright. Now 2.5, this value comes to 2.5 square. 2.5 square 6.25, 7.25, 1 divided by 7.25 over 0.3.5, 100 by 3 by 3 plus 5 into 0.007 plus 4 into 1 divided by 3.25 over 2.5, 0.053. Right. Now consider 3 plus 5 into 0.007 plus 4 into 0.053 into 100 divided by 3, which will come to 34.45 kilopascal. So this is the values at points beneath the point loads. Right. Now coming to the coming to this point, plan of a uniformly loaded rectangular area is shown below. Determine the vertical stress increase below the point A. So here we need to use the uh, theory where we have this charts, influence charts from Westergaard's analysis. Now here, first they have asked below point A. So how we do this is, first we consider point the rectangle corresponding to, because these assumptions are that for a rectangular area the stresses are calculated at the corner. All right, so these are for corners. So now we need to calculate, so the q, that is sigma z, will be q into I z. So I z will be calculated from this chart, for which we need to have m and n values. Iz, which is a function of m and n values. M is So the depth at which the stresses are required are, let z is equal to 5 meters. All right. Now m is defined as width by depth, and n is defined as length by z. So for this first case, for point A, sigma z at A, Q is 150 into I A. So for that, M A is, width is 2 meters and depth is 5 meters, which corresponds to zero point 0.4. N A corresponds to length. Length is 4 meters, with depth is 5 meters, which corresponds to zero point 0.8. So now let us take the chart. M and N is, MA is 0.2, 0.4, MB is, sorry, NA is zero point 0.8. All right. Now let us come to the point M. This is point 1, point 2, point 3, point 4. Let us draw the line accordingly. N is zero point 0.8. So the 0.8 line falls approximately here. So it is correspondingly IA will be approximately equal to 0.10, 0.105, 0.10, will be 0.102. All right. Now at below point C, which we have, that is 150 into 0.102. 50 into 0.102, which corresponds to approximately 15.3 kilopascal. Now, corresponding to this point B, let us calculate for point B. All right. For point B, sigma z point B is equal to 150 into IB. IB, MB will be, this is length, this is width. So here it will be 0.8 by 5, and NB will be 1.6 by 5. 0.8 divided by 5, it comes to 0.16. NB corresponds to 1.6 divided by 5, it comes to 0.32. Now coming to this chart, MB is 0.16, NB is 0.32. Now correspondingly 0.1, and this is 0.2, and hence 0.6 will be somewhere here. Right, and now it is 0.3, 0.32 will be somewhere here, 0.32 will be somewhere here. Sorry. 0.32 will be somewhere here. All right. Be approximately IB equal to 0.03. Here it will be 150 into 0.03. Should come to 4.5 kPa. Now coming to the point C, here what we have to do is we have to first extend this rectangle further. So this can be divided as, how can we write it as? So this is a rectangle what we had, which is 4 meters by 2 meters, and here at a distance of 1.2 meters we have point C. 1.2 meters we have point C, right? So we can extend this rectangle here. So what happens is that, so this is equal to 2 meters and 5.2 meters minus 1.2 meters and 2 meters. Alright. So at this point minus at this point. Alright. So first we will calculate here. For this we know M1 is equal to B by 2 by 5, which is 0.4. N1 will be equal to 5.2 by 5, which will be equal to 1.4. And this will be M1. Here the width will change because 2 is the length. So width will be 1.2 by 5, which will give us 0.04, 0.4, 4.0. 0.24, and N2 will be length, which is 2 by 5, which gives us 0.4. First we will consider zero point 0.4 by 1 by 4, 1.4. 0.4, which is M, 1.4, which is N. So for N, 0.4, 0.2, 0.3, 0.4, and 1.4 will be approximately here. You can take it as I is 0.13. It will come as 150 into 0.13, and here it is 0.24 and 0.4. 0.24 is M and 0.4 is N, which corresponds to 0.2, 0.24, and 0.4 comes here and meets here. I will be approximately 0.05. Right. Now this will be 150 to 0.05. Now calculating here, we will get 15 into 13, 195 minus 15 into 5, which we get 75. It gives us 120 kilopascal. 15 into, sorry, 3, which gives us 45. Into 0.3, 4.5. Sorry, 4.5. This is 150 into 0.05, 7.5. Gives us 12.5 kilonewton per meter square. This is the stress. This is how we do it in a what to say, uh, summative manner. So here, when the point is lying outside, please look for the uh, uh, rectangles, the number of rectangles that can be made in order to accommodate those points, and then we can such that its corner, the corner of the rectangle falls on the point of interest. So that is the major assumptions here. All right. So now moving to the next question. So three parallel strip footings, 3 meter wide each and 5 meter apart, center to center, transmit contact pressures of 200, 150 and 100 kilonewton per meter square respectively. Calculate the vertical stress due to the combined loads beneath the centers of each footing at a depth of 3 meter below the base. Right. So here first let us draw the diagrams here. This is a strip footing. This is 3 meter wide. This is another strip footing. 3 meter wide. This is another strip footing. 3 meters wide. Right. Now the center to center distances are, this is not the protocol since the available space is limited. I'm just doing it schematically. So it should be from above. So it should not cross any other measurements. So 5 meters and 5 meters. And the load acting here is, this is 200 Hauler kPa. This is 150 and this is 100. Right. Now we know that this is a strip footing. It is it is a line load of 3 meters and 1 meter and 1 meter. All right, kilonewton per meter of strip footing. That is the calculation that has been taken here. All right. So here it is a line load. So similar to the point load over superposition principle, we have to apply the line load superposition principle here. So here the relationship is sigma is equal to, it is fairly simple in this case, 2q by pi z into 1 by 1 plus x by z square power 2. All right. So x is the distance between the horizontal distance between the uh, 2 points. So here if you consider this as reference, x for this is 5 and x for this is 10. All right. Now z we know it as 3 meters. Now let us consider this as 1, this is 2 and this is 3. Now sigma z at the base 1 is computed as 2 into 200, x is 0, pi into 3 plus 2 into for second 150 by pi into 3, 1 by 1 plus x is 5, 5 by 3 square the whole square plus 2 into 100 by 3 pi into 1 by 1 plus 10 by 3 square the whole square. Now we take it as 400 by 3 pi plus 300 by 3 pi into 1 by 1 plus 5 by 3 will give us 1.66. This entire thing comes to 0.07 plus 200 by 3 pi. Now this comes to 0.006. Now let us take 100 by 3 pi outside. 4 plus 3 into 0.07. This will come to 0.21 plus, just a minute. This will be 2 into 0.006, so it will be 0.01. So calculating it, 4 plus 0.21 plus 0.012 into 100 divided by 3 pi, which will give us a value of 44.8 kilopascal. Right? Now similarly at below 2, so it will be 2 into 150 by 3 pi plus 2 into 200 by 3 pi divided by 1 by 1 by 1 plus x is 5 by 3 whole square plus 2 into 100 by 3 pi into 1 by 1 plus 5 by 3 whole square by 4 square. Now since here we are considering here, so x will be 5 meters from here and x will be 5 meters from footing 3. All right. Now we can consider it actually 100 by 3 pi into 3 plus 4 plus 2 1 by 1 plus 5 by 3 whole square the whole square. And now you can get it as 100 by 3 pi 3 plus 6 into 0.21, which corresponds to plus 3 into 100 divided by 3 pi, which will give us actually 45.2 kilopascal. Right. Now coming to number 3, you have 2 into 100 by 3 pi plus 2 into 200 by 3 pi. This will be 1 by 1 plus 10 by 3 square the whole square plus 2 into 150 by 3 pi divided by 1 divided by 1 plus 5 by 3 whole square the whole square. So in this case we will be getting 100 by 3 pi into 2 plus 4 into 0.12, 0 point, sorry, it will be, think, 0.012. 4 into 0.012 plus 3 into 0.21, which will give us 4 into 0.012 plus 3 into 0.21 plus 2 into 100 divided by 3 pi, which will give us a value of 28.41 kilopascal, right? So these are the values for the line loads, right? So hope these concepts are clear. So this requires multiple practices. You can go through any reference books for the practice of these problems. The more you practice, the more quicker you will be able to approach the problems. All right. So with this, we'll be closing the session for this particular week, and hope uh, this was a useful session. And I encourage the learners to attend the sessions actively in order to, uh, in a way, it will be useful for you also. And these sessions will take place every Saturday from 5 p.m. to 7 p.m. Unless there is a emergency situation for which the sessions uh, might be forfeited, and hence I encourage all the learners to actively participate and ask your doubts and involve yourself in solving the questions. So, so I will be closing this session and looking forward to meeting you next week. Thank you.